Hi everyone, welcome back to VLSI for everyone. Today's topic is implementing logic gates using 2:1 multiplexer. I chose implementing this topic because it's a classic freshman friendly question. I've also used this many times in interviews to help candidates settle into the conversation. My goal when I ask it is simple, give you a quick low pressure chance to show your fundamentals. Yet I see many students stumble, not because the idea is hard, but because they get nervous or try to overthink it. For interviewers, this question reveals more than the right answer. It shows how you translate Boolean expression into a hardware and how you explain your thinking, especially if this is your first technical interview. Mastering this shows that you can read a Boolean equation, map inputs to a 2:1 MUX, and communicate clearly under a little pressure. Let us first start with a 2:1 MUX. A 2:1 MUX has one selection line, let us call it S, and two data lines, D0 and D1. So the input to the selection line decides which input appears at the output, like output by. So if my selection line is 0, then D0 appears at the output. If my selection line is 1, then D1 appears at the output. We can also write it in Boolean form as y equal to S bar D0 plus S D1. So this is the Boolean expression for a 2:1 MUX. Now let us try to implement a NOT gate using 2:1 MUX. A NOT gate has one input and one output. Let us consider the input to be A and output to be Y. So the Boolean expression for a NOT gate, this is a NOT gate, is y equal to A bar, and the truth table for this is A, Y, 0, 1. So output is 1 and 0. So it is basically the inverted of the input is the output. Now how to implement a NOT gate using 2:1 MUX. Now let us make the 2:1 MUX. Now let us consider the input A to be the selection line of our 2:1 MUX. A is here and this is the output Y. So if the input A is 0, Y should be 1. So let us consider 0 and 1. So when the input A is 0, our data line should be 1. And if our input A is 1, our data line should be 0. Now, taking the Boolean expression for 2:1 MUX, so we have A bar into 1 plus A into 0. Therefore, output becomes Y equal to A bar, which is the Boolean expression for a NOT gate. Hence, if we make the data selection line for 0 as 1 and for 1 as 0, we can make a 2:1 MUX into a NOT gate. Now let us consider an AND gate. An AND gate has two inputs, A, B, and one output, Y. This is our AND gate. The Boolean expression for this, Y equal to A into B. The truth table is A, B, Y. Zero, 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 1. Now consider a 2:1 MUX. This can be D0. This is D1. Now since the AND gate has two inputs A and B and one output Y, let us consider one of the input A as the selection line for 2:1 MUX. Now coming to the truth table, if A is 0, Y is always 0. So now coming to the 2:1 MUX, if the value of A is 0, we can make the D0 as 0. And if the value of A is 1, then the output Y depends upon B. So we can make this D1 equal to B. So now coming to the Boolean expression y equal to a bar into 0 plus a into b. This becomes y equal to a into b. So this is how you implement a AND gate using 2:1 MUX. Now coming to the OR gate. It again has two inputs A, B and one output Y. So this is our OR gate. So Y equal to A plus B. The truth table for an OR gate is 0, 1, 1, 1. Now, if we want to implement an OR gate using 2:1 MUX, let us consider a 2:1 MUX. D0, this is D1. Now, since the OR gate has two inputs, let us consider one of the input A as the selection line for 2:1 MUX. Now, if the value of A is 0, my output Y depends upon the input B. So if B is 0, output Y is 0. If B is 1, output by Y is 1. So we can make the D0 as B. Now if input A is 1, the output Y is always 1, irrespective of the value of B. So here we can make this D1 as 1. Now coming to the Boolean expression for 2:1 MUX, Y equal to A bar into B plus A into 1. So it becomes A plus A bar into B. Using distributive law, it becomes A plus A bar into A plus B. Since A plus A bar is 1, Y equal to A plus B, which is the Boolean expression for an OR gate. Now coming to the NOR gate. Y equal to A plus B whole bar. This is my NOR gate. Now coming to the truth table for a NOR gate. This is 1. Now to implement a NOR gate using 2:1 MUX, we will take one of the input as the selection line for this 2:1 MUX. Now if the value A is 0, then Y is inverted of B. Because if B is 0, then Y is 1, and if B is 1, Y is 0. So we can assume Y is B bar. So we can make this D0 as D bar. Now if the A is 1, Y is equal to 0, because irrespective of the value of B, the output Y always remains 0. So we can make this D1 as 0. Now coming to the Boolean expression, Y equal to A bar into B bar plus A into 0. So Y equal to A bar into B bar. Now using De Morgan's law, A bar into B bar is equal to A plus B whole bar. So Y equal to A plus B whole bar. So this is the Boolean expression of NOR gate. Now coming to the NAND gate. So the Boolean expression is Y A B bar. This is my NAND gate. Now coming to the truth table. One, 0. Now again taking a 2:1 mux. Again taking one of the input A as the selection line for 2:1 mux. This becomes A. This is Y. D0 and this is D1. Now let us consider if A is always 0, then output Y is always 1. So Y equal to 1. Here you can see, irrespective of the value of B, the output Y is always 1. So this D0 becomes 1. Now if the value of A is 1, if the value of B is 0, then output Y is 1. And if B is 1, the output Y is 0. So we can say the Y is equal to B bar. So we can make this D1 as B bar. Now coming to the Boolean expression, Y equal to A bar into 1 plus A into B bar. Now we can, using the distributive law, we can say that A bar plus A into A bar plus B bar. Now since we know that A bar plus A is equal to 1, now it becomes A bar plus B bar. Now using the De Morgan's law, we can make this A bar plus B bar equal to AB whole bar, which is the Boolean expression for a NAND gate. Now coming to the XOR gate. This is A, this is B. The Boolean expression is Y equal to A B bar plus A bar B. So Y equal to A XOR B. So this is my XOR gate. Now coming to the truth table. Now taking a 2:1 mux. Again we will consider one of the input A as the selection line for 2:1 mux. This is D0, this is D1. If the input A is 0, then Y is equal to B, because if B is 0, Y is 0. If B is 1, Y is 1. So we can make this D0 equal to B. Now coming to, if A is equal to 1, then Y becomes B bar, because B is 0, Y is 1, and if B is 1, Y is 0. So this D1 becomes B bar. Now coming to the Boolean expression, Y equal to A bar into B plus A into B bar, which is basically an XOR gate. Now coming to the last gate, the XNOR gate. The Boolean expression Y equal to A into B plus A bar into B bar. So this is the XNOR gate. Now coming to the truth table. Now again, coming to the 2:1 mux, again we will take one of the input A as the select line for the mux. This becomes D0, this is D1. Now if the value of A is 0, the output Y becomes B bar. because if the value of b is 0, the output y is 1, and if the value of b is 1, then output y is 0. So we can make this d0 as b bar. Now if the value of a is always 1, then the output y is equal to b, because if b is 0, y is 0, if b is 1, y is 1. So we can make d1 as b. Now coming to the Boolean expression, y equal to a bar into b bar plus a into b, which is the Boolean expression of a XNOR gate. So this is how you implement all the logic gates using 2:1 MUX. Thank you everyone for watching, and please subscribe for more content.